Section 2.2 has to do with permutations. And a permutation is just an arrangement of some set of distinct objects. We saw some examples in the warm-up problems, but let's look at this example here. How many permutations are there of the letters A, B, and C? So this is just some set of letters, and we're wondering how many ways can we arrange those letters. It's only 3 letters. It doesn't seem like there's going to be too many different ways of arranging them, so we can probably just list them out alphabetically. A, B, C would be a permutation, but also A, C, B would work. That seems like the only possible way if we start with A. So then maybe let's look at starting with B. We could have BAC, or we could have BCA. These are going to be the only permutations that begin with B, so now I'm going to begin with C. I have CAB or CBA, and I think that's it. I can't really start with anything other than A, B, and C, so this looks like all of my different permutations. Notice, these are all arrangements of these objects, so we care about the order. Order matters in a permutation. In other words, we count these as different permutations because they're all listed in different orders. So how many are there? There's 6. But you can see how if we added more elements, it would start to get a little bit messy trying to figure out how many different permutations there are. Right, let's just scale this up a little bit and look at a set of 6 different elements, A, B, C, D, E, and F. How many permutations are there in this case? Well, what we wanted to do in the first case was sort of list out all the permutations that started with A. It's helpful to do this in some sort of organized way so that we don't actually miss any. But even starting with just A and looking at those, there's going to be a lot. There's a lot of different ways to arrange these last 5 letters here. You could do it alphabetically, A, B, C, D, E, F, and you could try to start switching things up, A, B, C, D, F, E, or A, B, C, I don't know, E, D, F, A, B, C, D, nope, E, oh boy, I'm already starting to get a little bit mixed up here. This is going to be really messy if I try to list them out by hand. So how could we try to use what we learned in the last section on the multiplication principle to help us come up with some quicker way of doing this without actually listing out all the different ways? Well, remember, when we're making a permutation, in this case a permutation of 6 letters, 6 distinct letters, we're making a choice, right? We're trying to decide how many different, or what letter are we going to put in the first spot? Are we going to put an A, a B, a C, or D, or E, or an F? And there's 6 options here. I'm going to put a 6 here just to represent that there's 6 options for the first letter in our string. Okay, so we choose a letter in our string. Now, what are our options for the second letter in the string? I can't really list them out anymore because the number of options you have here is, I guess, the actual options you have here depends on what choice you made here. If you had filled in this first spot with an A, you would have to choose a B, C, D, E, or F here. If your first choice had been a B, you would have to choose an A, C, D, E, or F here. Right, etc. If you had started with a C, you'd have an A, B, D, E, and F here. So the choices themselves are going to change based on what number you chose first, but you're always going to have 5 options left for the second spot because your next choice here is going to be one of the letters except for the one that you chose in the first spot. So even though the options themselves will change, you'll still have 5 options to choose from. It'll just be whatever you didn't pick in the first case. So we still have 5 options here. All right, and now using that same reasoning, for the 4th letter in our string here, it has to be anything other than the first 2 that you chose. So we'd have 4 letters left to choose from. Having chosen your first 3, the next letter has to be anything but those 3, so there's 3 options here. Now we've only have 2 left to choose from, so there's 2 options here. And if you've chosen the first 5 letters in your string, you only have 1 letter left to choose from, so you have 1 option here. Okay, so how many different permutations are there? It's this, 6 times 5 times 4 times 3 times 2 times 1, which I think is actually equal to 720. It's a good thing I didn't try to list them all, right? It grows very quickly. The more elements you add, the number of permutations grows very rapidly. You might recognize this expression from different math classes or any kind of probability class. When you have a natural number and then you multiply by each of the natural numbers less than that, we call it a factorial. Right, we would read this as 6 factorial. In general, n factorial is going to be equal to the natural number n times n minus 1 times n minus 2, all the way down until you get to 1, whatever, however far down the line 1 is. And so using this same general idea here, the total number of permutations of n elements is given by the formula n factorial. So we use the notation P of n. P of n means the total number of permutation of n elements. So there's n factorial many. And the reason for that is just exactly what we saw in this last example. For the first element, you have n many choices. Having made the choice of the first element in your permutation, you can choose anything except for that element here. So you have n minus 1 choices for the next spot, then you have n minus 2 for the third, all the way down the line. And since we're using all n of our elements, in the end there's only going to be one option left. So this product, n times n minus 1 times n minus 2, all the way down to 1, gives you that n factorial. Right, so this is really just an application of the multiplication principle. So let's look at another example. A talent show has 15 participants. How many ways can we select an order of performances? Right, well, you've got your 15 people. I'm gonna not so kindly call them person 1, person 2, person 3, all the way to person 15. They're not numbers, they're people, but I don't know their names. And so essentially what we're doing is we're choosing a lineup here. We're saying this is the first performer, this is going to be the second performer, the third, all the way to the end. Make sure you can read that. How many choices do you have for the first performer? It can be anyone from this set of 15 people. So you have 15 options here. Having chosen who goes first, there's only 14 people left to choose for the second, then 13, all the way down the line. All 15 of these people are performing, so in the end, there will only be one person left to perform last. And so there's 15 factorial many different performances. Go ahead and multiply that out if you want. It's a very, very, very big number. Too big for me to try to do right here, okay? Right, but this is really just a permutation of those 15 people. It's an arrangement of distinct objects, distinct people. All right, now, here's a extension question. What if it turns out that we only had time for 10 of those 15 performers? So let's say 15 people auditioned for this talent show, but we only have time for 10. How many ways can we choose an arrangement of 10 of those 15 performers? So how many ways to choose and also arrange, right, put in order 10 of those performers? We can use that same idea of the multiplication principle here. It's just, instead of having 15 dashes, we only have 10, right? Here's who's performing first, then second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. Okay, right? So these are representing who is performing and in what spot. How many options do you have for the first performer? Well, it can be any one of these 15 people. So there's 15 options. Having chosen the first performer, you have 14 options for the second performer. Having chosen that one, now you only have 13 left, and it just goes on down the line like this. Then 9, then 8, then 7, then 6, and then we're done. Right? So this isn't really 15 factorial because it doesn't go all the way down to 1. It looks a lot like 15 factorial, but we're missing the factors of 5, 4, 3, 2, and 1. Because 5 of those people just got cut. So how many different ways is this? Well, it's a lot. I don't want to multiply it out just like before, but I also don't want to have to like write it all out, because what if like 100 people auditioned and we only had time for 50 of them? I'd have to actually write out 50 different, dotted lines and multiply all those numbers down. It'd be really annoying to write. So what's a shorter way of writing this? Well, like we said before, this is almost 15 factorial, but we're missing factors of 5, 4, 3, 2, and 1. So start with 15 factorial, and then cancel out the last 5 factors, 5, 4, 3, 2, and 1. Because this is multiplication, if we want to get rid of a factor of 5, 4, 3, 2, and 1 in the numerator, I'm going to have to divide by 5 factorial in the denominator. So if you're not sure why this expression here, 15 times 14 all the way down to 6, is equal to 15 factorial over 5 factorial, just remember that you can express 15 factorial as 15 times 14 times 13, okay, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we want to get rid of everything after the 6, right? Because this is our answer here. This is the number of ways you can choose those performers. So to get rid of a factor of 5, 4, 3, 2, and 1, we'd have to divide by 5, and we'd have to divide by 4, and by 3, and by 2, and by 1. Right? The 5s then would cancel. The factors of 4 cancel, of 3, of 2, and of 1. That's why 15 factorial over 5 factorial gives you this, what we're looking for. Notice that we're getting rid of everything after the 6, and that's because out of these original 15, we were choosing 10, and so we would have 5 left over that we don't need. So really this is 15 minus 10 factorial in the bottom. Right? 15 minus 10 is 5, because we were choosing just 10 out of the 15. And this gives us an idea of why we would want to talk about a K permutation of N elements. So a K permutation of N elements is just an arrangement of K distinct elements chosen from a set of N distinct elements. This requires that K has to be less than or equal to N. It's not going to make sense otherwise. So this is really what we were doing in the last example. You're choosing K many elements, that's 10 many people, out of a set of N many elements, out of a set of 15 people. And so this suggests to us a formula for the number of K permutations of N elements. The notation that we're going to use is P of N comma K. This means the total number of K permutations of N elements. This is the number of ways that you can pick K elements from a set of N elements and then arrange them in some order. And the number of ways to do this is going to be N factorial over N minus K factorial. So subtract N minus K first and then take the factorial of that. Let's try to use that in one last example. A class has 26 people. If we must elect a president, a vice president, and a treasurer, and no one can hold multiple titles, how many ways can we do so? Well, let's first just think about this in terms of the multiplication principle. So we have 3 roles that we need to choose. We need to choose a president, we need to choose a vice president, and we need to choose a treasurer. There's 26 people in the class, so there's 26 choices for your president. But nobody can hold more than one position, so once you've chosen your president, you only have 25 options left for your vice president. So by the multiplication principle, there's 26 times 25 ways to choose the first 2. Or having chosen those first 2, now we only have 24 people left to choose from for the treasurer. So extending this using the multiplication principle, there's going to be 26 times 25 times 24 ways to choose a president, a vice president, and a treasurer. What does this really mean in terms of permutations? Well, out of the 26 people in the class, we're choosing 3 of them to distinguish as, title holders, and we care about the order that they're chosen, right? Choosing Abby and then Ben and then Cassie to be president, vice president, and treasurer is different from choosing Cassie, Ben, and Abby, right? The order that you choose them matters because it makes a difference whether one person is the president or the treasurer. So we can think about this as a permutation, a K permutation of N elements. So this is a 3 permutation of 26 elements because we're choosing 3 students from among 26 and we're giving them specific roles. So we're designating those roles so we care about the order that they're chosen. According to this formula, this should be 26 factorial, right, N factorial on top, divided by 26 minus 3 factorial. In other words, 26 factorial over 23 factorial. Does that make sense with the answer that we got over here? Sure, right? Because this starts off looking a little bit like 26 factorial, except once we hit 24, we stop. So we'd have to somehow get rid of all of the factors that come after 24. That's 23, 22, 21, etc. We can do that by dividing 26 factorial by 23 factorial. It's going to give you the same number that you get here. So however you want to think about solving this problem, you're really using the same idea, but in this case we used a formula to do it, and in this case we reasoned it out using the multiplication principle.